Hello, my name is Chien-Yung Tseng. I'm a PhD candidate at the University of Illinois, Urbana-Champaign. I'm gonna present the work, a turbulence-based two-layer model to predict sediment resuspension in vegetative flows. So this is a laboratory experiment work to study hydrodynamics of vegetative flows and its effect on sediment suspension. This is the outline of my presentation, which I will cover from the motivation, the background introduction, and the experimental methods. Then I will dig into the development of the model along with the experimental results, and finally give a summary. So as we know, sediment transport problem has been widely studied since early 20th because people has noticed the significance of sediments for water resources, ecosystem restoration, and landscape evolution in natural water environments, such as river, wetland, estuary, and coast. However, most of the previous studies focused on the bare bed open channel flows without considering the presence of vegetation. In fact, in this water region, vegetation is widely distributed from deeply submerged to emergent and from sparse to dense distributed, which can cause various impacts to environment under different scenarios. Therefore, in the recent decades, people realized that aquatic vegetation plays an important role in these regions and have started to study sediment transport in vegetative flows. So according to the previous works, people focused on how vegetation affects flows based on such key parameters of the flow and canopy, like stem diameter, volumetric frontal area, solid volume fraction, submergence ratio, and flow Reynolds number, especially for the array density and submergence ratio that results in different scales of turbulent eddies generated by vegetation. So there are two main scales of turbulence. The canopy scale turbulence, which is generated due to sharp velocity gradient on top of the submerged canopy, and the stem scale turbulence, which is generated by the vegetation stem due to the drag exerted by the stem that interferes the mid-flow structure. Also, the array density and the submergence ratio can affect the strength of both canopy scale and stem scale turbulence. So these turbulence can interact with the bed, resuspend the sediment, and change the suspended sediment concentration in water column. So in this presentation, I will discuss how the hydrodynamics alteration by the vegetation, which can be a function of the vegetation parameters, impacts on the sediment suspension. So our main purpose is to identify characterize the dominant processes driving sediment motion in vegetative flows and develop a model to predict sediment suspension in vegetative flows. So next, I will describe the experimental methods and the setup. So a series of lab experiments were conducted in a small-scale unidirectional recirculating plume, where the flow is driven by a rotating disc pump. A stress test section is 200 centimeters, and the width of the flume is 15 centimeters. So acrylic cylinders were used to mimic the high stiffness aquatic vegetation. 10 centimeter high sediment bed was set at the bottom of the channel, and two-dimensional planar particle image velocimetry (PIV) was used to measure the flow hydrodynamics, and the configuration of the canopy is set as staggered. We use crushed walnut shells as the sediment substrate because it's lightweight for the scaling effect to investigate sediment suspension in the lab. And the specific gravity of walnut shells is between 1.2 to 1.4, and the median sediment diameter is approximately 1 millimeter, which corresponds to 1 centimeter per second settling velocity. So here is the way we calculated sediments, the suspended sediment particles, which is by using a bright light to illuminate the measuring window and attached a white paper as the background behind the flume. Then the camera was put in front of the flume to record the images. Like in each image, sediment particles will generate black dots on the white background. Then by setting a threshold of intensity between two major groups in the histogram, readers can identify the sediment particles from the background water and finally converted the intensity values into binary values based on the threshold. So let's say for each pixel, if the intensity is lower than the threshold, it is identified as sediment with zero value. If the intensity is higher, then it is background water that is set as the value of 1. So by doing this, we can further calculate the concentration profile by doing time average and stringwise average of the binary values, which represents the existence probability of the sediment at this location. Then we set the value 1 as the bed and choose a location where it's close to the bed as the reference concentration. So next, I will discuss how we develop the model for the suspended sediment and present the experimental results against the model prediction. So to derive an SSC model for the vegetation, we first quickly review the previous model for the suspended sediments. As I mentioned previously, sediment transport has been studied since early 20th, but most of the previous studies focused on cases in open channel flows without considering the effects of vegetation. And Ross model has long been recognized as a useful model to predict suspended sediment concentration in open channel flows, which addressed that the bed shear stress provides the main lifting force to suspend sediment particles in water. And it is derived based on the equilibrium concept between the turbulence stress and the sediment settling. So according to the typical parabolic eddy viscosity profile in open channel flows, the SSC profile can be obtained, and where ZR here is the Ross number, which consists of settlement velocity divided by the bed shear velocity and the Volkmann constant. Then we're gonna check our method. Then we did 3 rounds of barebed cases without the vegetation on the different flow velocity and compared the experimental data to the Ross model. The profile generally matches with the experimental data, and the fitted bed shear velocity matches with the theoretical log-low velocity profile in open channel flows. However, for the vegetated cases, recent studies have shown that bed shear stress model doesn't work for predicting suspended sediment transport in flows with aquatic vegetation, since bed shear stress model only consider turbulence generated by the bed shear. Instead, we need to consider the total near-bed turbulence, including turbulence generated by the vegetation as well. And also, more studies show that the interactions between flow, vegetation, and the bed can generate fluctuating coherent structures, causing extreme peak values of the instantaneous bed shear stress and the time average bed shear coefficient around the vegetation. From the left animation of our experimental result, it shows the instantaneous velocity and sediment measurement from one of the cases. We can see some random burst from strong velocity components from the bed within the canopy and might be able to suspend more particles. So therefore, here we proposed a 2-layer turbulence-based model to predict sediment suspension for the flows with emergent vegetation, which takes all the turbulence components into account. From previous experiments in emergent vegetative flows, mean velocity profile is generally uniform above a certain height HB here. So from the bed due to uniform drag exerted by the vegetation to the mean flow, we call this region constant stress layer or constant velocity layer, where turbulence generated from the bed can be ignored, and sediment suspension is mainly supported by the stem turbulence. Then below HB, we call this region linear stress layer or effective bottom boundary layer. Within this region, the turbulence stress is assumed linear, just like the typical open channel flows, with a linear stress in the whole water column. However, we should not only consider the bed shear turbulence, but also turbulence generated by the vegetation and the flow coherent structures caused by the nonlinear flow vegetation bed interactions. So the near bed velocity bulge shown in the figure here is one of the features caused by the flow coherent structures, and which entranced fast-moving fluids with high momentum from the surrounding region into the wakes. Therefore, we applied the proposed 2-layer model to the emergent vegetative flows. As shown in the figure, the model generally captures the suspended sediment concentration and match quite well with the experimental data throughout the whole water column. There are 2 fitted parameters from the model, which might need extra models to estimate them: the effective near bed shear velocity and the effective bottom boundary layer thickness, HB. So here we provided two extra models to estimate these two major parameters. For the effective bed shear velocity, it is different from the general bed shear velocity that is calculated from only the bed shear stress. Instead, the effective bed shear velocity takes all the turbulence components that I mentioned previously into account. So the first one here is the bed shear turbulence, and then the second one is the vegetative turbulence, and the third one is due to the nonlinear stem flow bed interactions, which is the component caused by the coherent structures. Then for the HB, we followed the argument that within the effective boundary layer, TK production balances the dissipation, where the TK production can be estimated by the rate of work caused by the vegetative drag. And dissipation can be estimated by scaling with viscous forces. That is related to the mean flow velocity and the bottom roughness. So eventually we can get the final form of these two critical parameters. Then these two plots show the fitting results of HB and the effective shear velocity, which generally capture the trend of the experimental data and observations from previous studies in a certain range of flow conditions. So to summarize the work here, we developed a two-layer turbulence-based model to predict suspended sediment concentration in flows with emergent vegetation. We included coherent structures generated by stem bed flow interactions to calculate near-bed turbulent kinetic energy, and we derived models for effective bottom boundary layer thickness and effective bed shear velocity for the two-layer SAC model. So more details can be found in our recent publication in GRL. And of course, there can be some extended future work, like to extend the current emergent canopy model to the submerged canopy flows. So as shown in the plot here, blue dashed line represents the vegetation height. And we can see that below the line within the canopy, the model for emergent vegetation works well, but not for the region above the canopy, because the canopy scale vortices generated by the velocity gradient can modify the sediment suspension. So the emergent model should be first modified into 3 or even 4 layers to include the mixing layer on top of the canopy and the outer region above the mixing layer toward the surface for the submerged cases. So finally, I would like to thank my advisor, Dr. Rafael Tinoco, and our EEL research group members. So acknowledgement also goes to NSF Career Award for supporting this research, and the Taiwan UIOC Fellowship for supporting my PhD study at University of Illinois. And finally, I'm happy to take comments and have more discussions. So here is my contact information. Please feel free to contact me if you would like to know more details about our work. And thank you very much for listening.